So good afternoon all. I welcome you all again for the another lecture of say electronics, basic electronics. We were working on basic components like resistances, capacitances, and inductances. We have completed resistors, and we have started with capacitor, I guess. So, am I audible? My voice is clear. Hello. If anybody can reply, yeah. Thank you, Vita. Thank you. So now let me share my screen. Right. So yes, uh, we can start with this. Just hold it for a second. So yeah, I guess my screen is visible to you all. So welcome again and welcome for another lecture of say basic electronics. Myself, Dr. Andy Meshram, Head of Department Electronics, Sri Mathura Das Mohta College of Science. And today we are going to continue with the another lecture that is for the capacitor. So I guess I have introduced you what is a capacitor, but let me refresh it what we have learned in the last class. So capacitor is like this. The basic definition that I told you, that two conducting plates separated by a dielectric medium is called as a capacitor, right? So two conducting plates separated by a non-conducting medium is called as a capacitor. These plates act as a these plates act to store the charges on these plates, right? So this is the basic concept of the capacitor that we have studied. A capacitor in which we are expecting to store some energy and in the form of charges, right? So we are moving the charges on one of the plate, and the other charges are going to be deposited on the other plate. So yeah, that is the main job of a capacitor, and it's just like analogous to the spring element of a mechanical system. It just discharges it. So while storing it, we restore the spring like this, and it discharges when we release the spring, right? So it is like that. So it's just like that, and we are storing the electrical pressure for periods of time. So we are putting it there, and when a capacitor has a difference in voltage, electrical pressure across its plate, it is said to be charged. Yes. So as I told you, when we place a spring like this, so this is a pressure that we have built, and when we release it, when we put pressure on this totally, then it is called as a charge, right? And when we release it, it is called as a discharge. A capacitor is charged by having one-way current flow through it for a period of time. We put it to a power supply like this in the opposite. In the next slide, we are going to show you that construction. Yes. So this is that construction of a capacitor. So we are having two plates, and when we apply this polarity, this is positive and this is ground, and when we apply the polarity or a power supply to this plate, then these plates get charged. So the positive terminal is charged over here, positive terminal is connected over here, and oh, sorry, and hold it for a second. Yeah, so the positive charges are going to be deposited on this, and the negative terminal of the battery is connected to the lower plate, and therefore negative charges are going to be stored on the negative. So plus Q and minus Q charges. So this should be minus, yes, negative charge gained due to electrons, right? And this is the direction of electron displacement. So this is in the opposite direction. So this is how a capacitor works. A capacitor is constructed using a pair of parallel conducting plates separated by an insulating material. Insulating material means a non-conducting medium. I have told you that if I put a paper in between this two plates, then it becomes a paper capacitor. Similarly, when we put some oil in that, which is a non-conducting medium, in between that two plates, then it becomes a oil-filled capacitor, right? Similarly, we can have an electrolyte as a non-conducting medium in between that, so it becomes an electrolytic capacitor. Similarly, we can have a ceramic over there, so ceramic capacitor will be formed. And if we put rubber, which is again a non-conducting medium, then a rubber capacitor can be formed. And there are n number of capacitors where we can use different sorts of non-conducting medium or an insulating medium. And if you put in between that two plates, then automatically it becomes that capacitor. So we can design your own capacitors also. So I will show you those capacitors. There are n number of capacitors, so there just you have to think in that direction that this can be formed of a capacitor, right? One capacitor I will show you that in which the earth acts as a one plate. Just see the strength. Okay, Manish, you have in the downward direction you will have a menu coming over there, and there it might be written that join with audio. So just press it, then you will be able to hear that, right? So you'll be able to hear the voice. Kindly do that, Manish, so that you will be able. Yes. So what I was telling you that the Earth is acting as one plate, which is supposed to be more ground, and the clouds which are floating over it act as the another plate. So these forms a capacitor, right? A capacitor sort of a structure. So when the clouds are moving from one point to the other, they go on storing charges, right? So while movement, they are storing the charges. Actually, they are electrostatic force of attraction, and due to that, when these charges are overflowed on a cloud, then it discharges, and it discharges through the lightning, right? So that is one sort of a charge capacitor, right? So then this is how the charges are being stored on one of the plates, and this is how they are being discharged. So whenever the lightning is there, we say like a bijli gir gayi. So bijli jo girti hai, actually those are charges. And if else in future we are able to store that charges somewhere in some battery, like, so we will be able to say have electricity of 1 month to whole Nagpur city. So that is the power that discharge of that lightning has. But we are not, we are still unable to store that charge. That is a field of research also, one of. So this is a sort of a capacitor. So think in that direction, you will be able to find that there are n number of capacitors floating around in the environment. So the main concept is whenever we find two plates which are separated by a non-conducting medium, it forms a charge. It forms a capacitor. So this is the definition. When the two plates of a capacitor are connected to a voltage source, as shown in this diagram, so are displaced from one side of the capacitor to the other side, thereby establishing an electric field. So here we can have an electric field over there in the capacitor, and since it is connected to the positive charge, the upper plate is going to be deposited by positive charges, and vice versa in the lower plate is going to charge with the negative charges. So the charges continue to displace in this manner until the potential difference across the plates is equal to the potential of the voltage source. So whatever voltage we have put over here, unless that voltage appears on these two plates, it will go on charging, right? As soon as this voltage is equal to this voltage on this plate, then it is supposed to be fully charged, right? And whenever we want to discharge, we just need to reverse the polarity. Then the capacitor is supposed to be discharged, right? So this is the basic construction of a capacitor, that two conducting plates separated by a dielectric medium, and while connecting a voltage source, we should connect it positive and negative. So it depends on the polarity, right? This is water analogy, pipe analogy circuit. If you need to understand what it implies is, we are having two plates over here, the rubber diaphragm sealing the center of the pipe. So this is sealed one, but it is a rubber, and this is a plunger. Hopefully this can move from one point to other, and a water is filled inside it. So whenever we try to push this plunger towards this diaphragm, since it is very elastic, so it will try to float, and it will try to elongate along the side of this. So it will generate some pressure. Similar is the case for the charges. So whenever the charges are being stored, it becomes bulky, and the pressure is applied as far as voltage is concerned. So here we are putting a pressure. There, the voltage is supposed to be stored on those capacitors, right? So this is the analogous circuit of capacitor and water pipe. You need to understand. And this is one more example that this is the same example that we are studying. So if you put it here in a small bore pipe, then there is a large capacity but low pressure, low capacity but withstand high pressure, since the bore of that is little bit larger, and this is very large. So as we go on increasing the size of that, more charges can be stored. That is what we mean to say over here by using the same concept of a capacitor. So when the plates are of very high size, very large size, then more charges can be stored on that. So that is one of the basic characteristics of say capacitor. I guess this slide is not visible. Just give me a moment. I will make it just so that black. Yeah. So I guess it is visible now. So there is one more slide, I guess. No. So yeah, this was done. This was there. Okay, this was the yeah. So this was the yeah. So the charge accumulated on a capacitor, VI characteristics. Whenever the charges are being say accumulated or stored on a capacitor plate, that is directly proportional to the voltage applied across those plates, right? Then by that we can say that Q is directly proportional to V, and if you want to may equate that, then we have to put a proportionality constant. There we can say that Q equal to C into V, right? So now here the proportionality constant, that is C, is called as the capacitance, and the unit of capacitance is farad. So where C is the constant of proportionality and is called as capacitance, and the unit of that capacitance is farad. So VI characteristic of a capacitor is obtained by computing this equation. So we can have a different sorts of equation in different forms. So that can be given over there, like dq by dt, ddt of q into c into v. So we'll have dq by dt, c dv by dt, and by that we can find the current. Dq by dt is nothing but rate of flow of charges, that is current. So I into dt is equal to c dv by dt. So alternately we can integrate. So alternately we can integrate that whole equation, and we can have v dt Vt equal to 1 by C integration of 0 to time t, that is the time limit that we are providing, I t into dt. So this is that equation of the capacitor, or the voltage which is being stored on a capacitor when we apply a voltage source across a capacitor, right? The next one is the capacitance formula. Now, what is the formula for that capacitance? If we have two plates which will have a certain dimension, that is some area, and say a distance between them, so what will be the formula for that particular capacitance? So we can calculate the value of that capacitance by this formula, that is C equal to epsilon 0 A by D. I guess this equation you might have derived in your 12th class, because it has a whole chapter on this capacitor. So you might understand, and if you don't recall this, go through that notes, and if time permits, we will try to solve. We can also define that, but it has a whole chapter of electrostatic, I guess, and in that we have derived this equation, C equal to epsilon 0 A by D, where epsilon 0 is the permittivity of free spaces, and A is the plate area. This is the area of that plate, and D is the distance between these two plates. So as the distance is inversely proportional to the capacitance, whereas the area is directly proportional to the capacitance. So if there is a large area, surface area, so we'll have a large capacitance, right? So C is directly proportional to the area of cross section or area of the plate, and D capacitance is inversely proportional to the distance between the plates. So this is the equation, and often we use this is G, that is A by D, that is the geometry factor for other types of a capacitor as well, where the distance, where the area and distance are kept constant. So we take it as a G, so that can be taken, and we can calculate the dielectric of a material by using this proportionality C equal to K epsilon 0 G, where K is supposed to be the dielectric constant. Usually K is greater than 1. So that is the dielectric constant of the medium, right? So that is a part of research, so it doesn't suit you. So we have just to remember this definition, that is C equal to epsilon A by D. आप जब आगे पढ़ोगे तो शायद आपको ये आगे काम में आएगा, डाइलेक्ट्रिक कांस्टेंट और क्या होता है, बट एक्चुअली हमको सिर्फ इतना समझना है कि ये दोनों प्लेट्स जो है ये कोई तो भी नॉन कंडक्टिंग मीडियम से सेपरेट किए हुए हैं, राइट? तो उसका भी एक कांस्टेंट होता है नॉन कंडक्टिंग मीडियम का, दैट इज कॉल्ड एज अ डाइलेक्ट्रिक कांस्टेंट। ये हम लोग आगे पढ़ेंगे, हमारे को अभी इसकी जरूरत नहीं। मेन फॉर्मूला हमारा जो है C इक्वल टू एप्सिलॉन A बाय D ये है, जिसमें epsilon 0 is called as the permittivity of free space, and A is the plate area, D is the separation distance of the plates, that is distance between the two plates, right? So this is the formula for capacitance that we have studied. So this is the symbol of that. So we have two equal plates, so that's why we draw two equal lines over there. And if you see the symbol of a voltage source, so one line is greater and the another line is smaller to that. So we use this because this is at a higher potential. Therefore, we have a large, big line, and the small line represents that it has a small potential voltage. Therefore, we call that. Manish, beta, ये थोड़ा मिटा दो. Manish, रब कर दो बेटा ये सब. So kindly don't do anything on the screen, please. ये सबको दिखता है, and since we are going to load it on YouTube, so Manish, please, yeah, thank you. So this is there, and these are the some of the capacitor symbols that I have shown you earlier. So this is the simplest capacitor that we have. This is a fixed capacitor and it doesn't have a polarity, this first one. So that's why it is called as a fixed capacitor. Whereas this is called as a polarized capacitor. Whenever we are going to use the electrolytic capacitor, implies that it has a positive terminal and a negative terminal. So we have to connect it to a circuit accordingly. So we have to connect the positive terminal properly and the negative terminal properly to a circuit. Otherwise, what it will do? It will blow the capacitor, right? So remember this. Ceramic capacitor does not have any polarity. You can put it anyway, so it won't matter. But for electrolytic capacitor or for higher capacitors, we have to remember that it might have a polarity. So whenever we have to show in a circuit the symbol of a capacitor where we are having polarities, then we need to show like this. So this is a polarized, this is positive, and this is a negative terminal. And the other one is the variable capacitor. The third one is variable, means where the capacitance of a capacitor can be increased or decreased accordingly. We are going to study in the last slide what are the variable sorts of capacitors. So these are the symbols of capacitor. One is fixed capacitor, the other one is polarized, which means it has a polarity, positive and a negative. And the third one is a variable capacitor, where this arrow shows that it can vary from 0 to in whatever with the capacitance is there, right? So we can vary this capacitance like gang condensers and all. So this is, and then these are some of the capacitor variations. So this is what I was talking. This is a ceramic capacitor. Implies that the dielectric medium or a non-conducting medium which is used between these two plates is ceramic, right? So where the ceramic is used, these are called as ceramic capacitor. We have a lot more ceramic capacitor over here. Whenever offline classes will start, I'm going to show you all those ceramic capacitors and how to calculate the values of those ceramic capacitors, right? This doesn't have any polarity. These are very cheaper with respect to electrolytic capacitors, and they are very sensitive to temperature, and also these are some of the drawbacks of that. So these are basically used for a bypass capacitor, like in common emitter, common collector amplifier, whenever we need to connect two amplifiers together. You will come to know. Then we use these sorts of capacitors. The other one are called as, yeah, these were the electrolytic capacitors. These are axial lead capacitors, the same electrolytic capacitor, but having two leads on two sides. And this is radial capacitor, which means that they are having leads on the one side only. So if you are able to see, there are positive and negative terminals. And similarly, negative terminals are a little bit smaller with respect to the positive terminals. So remember this whenever we'll come and see the capacitors, then we'll know. These are called as electrolytic capacitors, and they have aluminum tantalum, tantalum electrolytic capacitor, we call these as, and they are having larger capacitance as compared to ceramic capacitors, and they are mostly polarized. They have polarity positive and negative, greater capacitance but poor tolerance when as compared to non-electrolytic capacitors. So they are, the tolerance means the variation of capacitance is slightly higher as compared to ceramic capacitor, and they are bad temperature stability, high leakage, short leads. So these are some of the drawbacks of this electrolytic capacitor. Then these are some more capacitors. These are called Miller capacitors. They are very popularly, these are also non-polarized, reliable, expensive, and non-leakage, poor temperature stability, means as the temperature or increases or decreases in the environment, that capacitance also varies accordingly. These are called as mica capacitors. So mica is placed in between the two plates, and it forms the mica capacitor. They are accurate, they have low leakage current, and these are small capacitors. Still, they don't have any polarity with them. So these are some sorts of capacitors. Then, yeah, how to calculate the capacitance? Basically, ceramic capacitor. So whenever we have a ceramic capacitor, you will be having these sort of say numbers written over there. It is mentioned here 104K, right? 104K. So the first figure of value, second figure of value, this is 10, and this is the number of zeros or the multiplier. So as we have done it in the resistances, the first band, second band, and the third multiplier band. Similarly, we will have these three, and then we have the K. This is for the tolerance, as we have told you. So if we need to calculate what is the value of that, and this comes under the pico. So this is 10, the first and the second, 10, and this is the multiplier, that is 10 raised to power 4. And since it is a ceramic capacitor, we'll always take it in picofarad. So pico, I guess you remember this. Pico means 10 raised to power minus 12. Remember this, 10 raised to power minus 12, right? So now the total number becomes 10 into 10 raised to power 4 will give you 10 raised to power 5, and pico means 10 raised to power minus 12 farad. And if you further resolve this, then it will come out to be 10 raised to power minus 7, right? So 10 raised to power minus 7 farad, and if I just put one decimal point, so I will have 0.1 into 10 raised to power minus 6 farad, and if I write 10 raised to power minus 6 is, if you remember it, it is nothing but micro. So I can write the total value of this is 0.1 microfarad capacitor, right? And the tolerance is plus minus 10%. So if there is a K, then we take it as 10 raised to power 10% of tolerance, means plus minus 10%. So it might vary from, say, 100. I have told you that if the value of the capacitance is 100, then it may vary from 110 to 90 to 110. So plus minus 10% of the exact value. So that is the tolerance. So the K denotes the tolerance over there. So, and another example to calculate this capacitor is 103M. So the label represents a tolerance. So 103, I guess you understood. 10 means 10 into 10 raised to power 3, right? And whenever there is M, then the tolerance is plus minus 20%, right? Since it is 103, means it is 0.01 microfarad. This is how it has been calculated. So 10 into 10 raised to power 3 picofarad, that is 10 raised to power 4. Earlier it was 10 raised to 104. Therefore, we have taken it 10 raised to power 4. Here it is 3. So the multiplier is 10 raised to power 3. 10 raised to power 4 into 10 raised to power minus 12, that is 10 raised to power minus 8 farad. And if you just shift the decimal point, then we'll have 0.01 into 10 raised to power minus 6 farad. So we'll have 0.01 microfarad capacitor. Lastly, we need to just touch the portion of variable capacitors. Now remember, what is variable capacitor? The capacitance of capacitor can be changed by using some sort of arrangement. Then that particular capacitor is called as a variable capacitor, right? For example, the devices that can be made to change the capacitance values with the twist of a knob. So if you are able to see, this is a particular arrangement that we'll have, and these are some of the rotatable plates, and they are moving. And these are some of the stationary plates which are square in the square form, and these can be moved with this knob. So as you increase or decrease the volume of say a system, similar is the portion of this knob. So as you go on increasing or decreasing, the area of overlapping over here in these plates will go on increasing and decreasing. Accordingly, the capacitance of the capacitor can be varied, right? So these are called as the variable capacitors. Air variable capacitor consists of two sets of aluminum plates, stator and rotor. So these are called as stator, and these are the rotor plates that mesh together but do not touch, often used in frequently adjusted tuning applications. So we know that earlier there were radios which were tuned, like, so we have, if you need to tune some band, so we have to rotate those knobs, and we have to set at a particular channel, right? So accordingly, we used this, yeah. So we were using this sort of connection for telecommunication system. And these are some of the streamer sort of capacitors where we will have only so we will have only a pot like a screwdriver where we can rotate and we can vary the capacitance, right? So these are called as streamers. So they are very small in size comparatively with respect to this sort of say capacitors. These are very big in size, and their arrangements are also very difficult to make. So these were used earlier. Nowadays we are using these on circuits. So these are called as streamers. Even in potentiometers, even in resistances, variable resistances, we have some streamers also, right? So these are some of the capacitors that we have studied. I guess you have understood the topic, and I guess that you will ask any questions if you have. So just I will just brush it. Today what we have done, yeah, today we have started with the capacitors. So we have studied the capacitors, and in that we have studied first the concept of capacitors, that the capacitor is an energy storage element which is analogous to spring element of a mechanical system. It can store electrical pressure, that means electrical voltages, charges basically on the plate, and accordingly they can be used. So this was the arrangement of that. Two conducting plates separated by a dielectric medium with a particular distance, and whenever we connect to a voltage source to it, then the charges are going to be stored. The positive charges are going to be stored where positive polarity is connected, and negative charges are going to be stored where negative polarity is connected. So this was a water analogy circuit I've shown you, and these are some of the formulas which are very essential for as far as capacitance are concerned. Q is directly proportional to V, and Q equal to C into V. Then we have in the form of current, so IT equal to C dV by dt, and this was the formula that voltage with respect to time can be written as 1 by C integration of 0 to T I C into dt, where T is the time. With respect to time, the current is going to vary. Then we have capacitance formula, that is C equal to epsilon A by D. This is for a parallel plate capacitor where epsilon 0 is the permittivity of free spaces, A is plate area, D is separation d is the distance between two plates, right? So this was the formula that we have studied, and this is the basic symbol diagram of the capacitor. Then these are some of the symbols. This is fixed capacitor, polarized capacitor, variable capacitor, and these are some of the types of capacitors that we use: ceramic capacitor, electrolytic capacitor, and then we have Maillard capacitor, mica capacitors accordingly. So we have all sorts of capacitors. Then we have heard about how to calculate the values of capacitance. I guess you have understood that how we have calculated the first figure, second figure, that is joint, that is tan, and this is the multiply, 10 raised to power 4, and K stands for the tolerance, that is plus minus 20, 10, and if it is M, then it is plus minus 20. So, and the value is taken in picofarads for a mica capacitor. So we have 10 into 10 raised to power 4 picofarad. Pico means 10 raised to power minus 12. And yeah, so we have calculated, we have solved this, and then we have 10 raised to power minus 7 farad. We have shifted one decimal point, so we have 0.1 into 10 raised to power minus 6 farad, and my 10 raised to power minus 6 can be written as microfarad. So 0.1 microfarad. So this is the value of that capacitor. Similarly, if you have this sort of a capacitor where it is written 103 M, so M stands for, it will have a plus minus 20% tolerance. So this is how we have calculated, and this is for the variable capacitors that we have, or gang capacitors, gang condenser we call it. So these are some sort of capacitors where the capacitance can be varied according to the say overlapping of the plates, right? I guess this much is over for today. So if you have any queries, the class is ready to get some questions, I guess. So if you have any questions, you can ask. You can unmute yourself and you can ask. So I guess there are no questions. Do you have any questions? Okay. So it implies that there are two things. One, you have understood everything, or the second part is you have not got anything. So there are no questions. Okay. So whatever, I'll be still uploading this video on YouTube. Go through my YouTube channel and view that videos. And if you have any difficulties, put some comments on that. So I will be happy to resolve those comments. So by now today, thank you very much for this attending this class. And I guess that more students will attend this class and ask the other students who are in who are connected to you to kindly join the class. By now, thank you very much. Take care, be safe, stay home, stay safe, and take care. See you soon. Good day.